Hello. In this video, we're going to talk about derivatives and integrals of vector functions. The good thing is, it's not very different from what you already know about derivatives and integrals. I wouldn't say bad thing, but more difficult part is that every time we take a derivative or an integral with vectors, we're going to have to do it multiple times. But it's not that bad. So let's say we're back with our vector function r of t is equal to a vector with components f of t, g of t, and h of t. So those are all functions, which means that if we were to take the derivative of r of t, that would give us r prime of t. We could also write it as dr hat dt is equal to r hat prime of t. Then what that's going to do is it's going to send a d dt, a derivative with respect to t, into each of the components of the vector. And so you'll find three derivatives. Now the derivative vector function is going to run tangent to the original vector function at a particular point or just in general. So in general means that our derivative function will be a function. And in particular, like at a point P, means that we will plug in a t value and get like a number or a vector with numbers in it. So we've got this great picture down here, and every time we cover derivatives, we have to talk about the definition and kind of the geometry of what's going on. In this picture on the left, we're looking at the secant vector, PQ, and you'll notice that PQ is basically a vector that is connecting 2 points that are on the curve C. And so P is defined as r of t, and Q is defined as r of t plus h, and then the difference between them is r of t plus h minus r of t. That would give us a secant vector, PQ. Now, if we were to divide that by h and then go ahead and take a limit, so here now I'm looking at the picture that's on the right with PQ, we can imagine Q kind of traveling along the curve and getting closer and closer and closer to P until we get what we call the tangent line, or the tangent vector in this case. And this right here, this is r prime of t, in case that's not clear on the screen. Okay, and so whenever we find a derivative vector, we have to remember that that derivative vector is tangent to our original vector at any given point on the curve. Now, a derivative vector, so r prime of t, has magnitude. And that's not like a bad thing or anything, but if we need to use r prime of t to calculate some things, and I can't really get very specific on what some things are yet, but it'll come up throughout the semester. So if we need to use r prime of t to calculate some things, its magnitude will mess up some calculations, not all. Okay, but it's something to consider. And so it doesn't mean we just avoid taking the derivative or using a tangent vector. It means that maybe we need to look at a new thing. Maybe we should look at a unit tangent vector. So all that is we call it big T of t, okay, the big tangent vector, and it's a unit one. And in order to make anything into a unit vector, we divide out the magnitude, and that just takes away all the length aside from 1 unit of length. And so if we take r prime of t and we take the magnitude of r prime of t and we find the quotient, that is going to give us the unit tangent vector t of t. Okay? Let's see. The unit tangent vector will point in the same direction as r prime of t, and that's because it's just going to be the same vector with no magnitude, just be a little bit shorter. So, if you wanted to see a little picture, let's say that this was a picture of r prime of t. then we could say that in green here, that is t of t. That's our unit vector. Just dividing out all of the length that we don't need. Okay? Let's see. Down below we have an image, and what's on here, it's a curve. The black curve is on there. And then we see little t vectors. Those are all unit tangent vectors. And then we also see n's and b's, and the n is the unit normal vector. Now notice that it is perpendicular to the t vector. So the unit normal vector is just a vector that is perpendicular to the curve and the tangent vector, since they're pointing in the same direction. Let's see, so it's a unit normal vector, and we don't learn about it yet, like how to calculate it. We are going to cover that in the next section. But, real quick, we could just say what it is. The normal vector is going to be the derivative of the unit tangent vector, which that derivative will no longer be a unit vector. So we'll need to divide out whatever magnitude got introduced by taking the derivative of it. That would be the unit normal vector. And then the third vector that's on there is the b vector. It's called the binormal vector. And it is also perpendicular to the other two. It's perpendicular. And you can't see it on this picture because we have no depth on here. So we'll talk a little bit more about those in the next section. But this is just kind of a cool picture to look at of the different vectors that we may calculate when we're finding derivatives. Now, where it's important is probably in physics and maybe in some engineering classes later on. These are called the TNB or BNT or NTB. People put them in different orders, but they create a set of three vectors that are all normal to each other, or we use the words orthogonal, normal, orthonormal. They're all perpendicular to each other. And so in 3 space, that's possible. Like if you think of the x, y, and z axes of the octant, those are all perpendicular to each other as well. Like the I hat, j hat, k hat standard basis vectors that represent x, y, and z, those are all perpendicular to each other as well. Well, the TNB also has that same relationship. Okay, let's move on and find some derivatives. Okay, I'm already seeing a typo in here. Hold on, let me just cross this out because it shouldn't say find the derivative of r prime. It should say find the derivative of r of t. And r of t is equal to a vector with components 1 plus t cubed, t e to the minus t, and sine of 2t. So if I want to find my derivative, I'm going to need to take dr dt, which that'll give me r prime of t. And it means that I need to send a ddt through to each of the components. And so I have ddt of 1 plus t cubed, ddt of t e to the minus t, and ddt of sine of 2t. All right, let's send those ddt's through. We have to remember all of our derivatives now. Derivative of a constant, when ddt runs through the 1 plus t cubed, derivative of 1 is 0. Derivative of t cubed is 3t squared. That's done. The derivative of t e to the minus t, that will require a product rule. So derivative of the first times the second plus the first times the derivative of the second. The derivative of the first, that'd be the derivative of t, it's going to be 1, times the second, e to the minus t, plus the first times the derivative of the second. The derivative of e to the minus t is e to the minus t times the derivative of minus t, which gives us a minus 1. Okay. And the derivative of sine of 2t is going to require the chain rule. We take the derivative of the outside sine, and we get positive cosine of 2t, and then times the derivative of 2t, that's going to give us a 2. So now we just clean up our mess a bit. This gives us 3t squared in the first component, and then the middle one will be e to the minus t minus t e to the minus t, and then the last component is 2 cosine of 2t. Okay, so that's our prime of t. Now they're asking for a little bit more. Find the unit tangent vector at the point t equals 0. Okay, I want to go through this because so often we can either make a mistake and or we can make a problem take longer than it needs to. Number one, if you're finding derivatives, don't plug in numbers first. You have to find the derivative first and then plug in the number, okay? The second thing is, when you're finding a magnitude, you can find a magnitude of functions or you can find a magnitude of a number. Like plugging in a number and then find a magnitude of your vector. It's easier to find the magnitude of a vector that has numbers in it than it is to deal with the functions. Here's what I mean. So the next thing they're asking us to do is to find t of t at t equals 0. So that means I need t of 0, which will be equal to r prime of 0 divided by the magnitude of r prime of 0. That means I am not going to find the magnitude of the vector function. I'm going to find the magnitude of the vector function evaluated at a point first. So let's do that. R prime of 0, I need to go into the derivative I just found, and everywhere there's a t, I'll plug in a 0. 3 times 0 squared, e to the 0 minus 0, 2 cosine of 0. It looks like in the denominator, I'm going to have to clean this up. So I'm going to write my numerator over again to clean it up so I can see what's going on. The numerator, I get 0. E to the 0 is 1. Cosine of 0 is 1, so the third component is 2. So I'm dealing with a vector that has components 0, 1, and 2. That means my magnitude is the square root of 0 squared plus 1 squared plus 2 squared, which gives me a total of the square root of 5. And that's it. That's all I got to do. I could have made this so much harder on myself if I had tried to find, now I'm going to write this, but then I'm going to erase it. Well, maybe I will write it, and then it'll just be a message. Don't do this. Don't find the magnitude of r prime, because here's what it looks like. 3t squared all squared plus e to the minus t e to the minus t all squared plus 2 cosine of 2t all squared. I mean, I can do it, but it's just ugly. Like, this is a bit painful. It is better to evaluate at the number or at the given number and then find magnitude. It'll just save you some frustration, possibly. Okay? All right, next one. Find the parametric equations for the tangent line to the curve with the given parametric equations at the specified point. Okay, we have some curve in space. We have a point on our curve in space. If we find the derivative and evaluate it at the point, we're going to have some r prime of, and I'm going to have to figure out what t is equal to. So some r prime of t naught. I'll call it t naught for now. That way we know it's a number and it's not a variable. So that let's let's say that this is what we have. We have a vector that is running tangent to our curve, but they're not asking for a vector tangent to the curve. They're asking for the tangent line to the curve. That's a little different. So the tangent line is a line. So it'll have the form r of t is equal to r naught plus tv. So we've got to get those values. Looks like we have an r naught. The point that we were given, that'll work. That can be our r naught. But what we don't have is v, a direction vector. It turns out the direction vector v is parallel to the tangent line and r prime of t naught is parallel to the tangent line. That means we should go ahead and let v, our direction vector, equal r prime of t naught, whatever that happens to be. Okay, so those are the things that we need to find. All right. First things first, I have my r naught. It's going to be 2 ln of 4 and 1. That was given. But what I don't have is a t naught value. So to find t naught, plug the given point 2 ln of 4, 1 into the parametric equations. And solve. Now, it's actually not too big of a stretch because we've got one component that is super nice, z equals t. And in the point, z is equal to 1. So this tells me that t is equal to 1. I can check it in the others. In the others, if x is equal to 2, and I square both sides, then I've got 4 is equal to t squared plus 3. I'm going to move the 3 over. T squared is equal to 1. T is equal to plus or minus 1. I'm going to go with 1, just positive, because z was equal to 1. If I let y equal ln of 4, then I have ln of 4 is equal to ln of t cubed plus 3, which means 4 is equal to t squared plus 3. Again, t squared is 1, and t is plus or minus 1. The z is equal to 1 pins us down to just the positive solution and not the negative solution. Okay, z equals t is given, and z equals 1 in the point. Therefore, t naught is equal to 1. So that's what we're going to use. All right, we need to find r prime, or the components evaluated. So let's go ahead and do that. In parametric form, x prime of t is equal to, now I have to take the derivative of the square root of t squared plus 3. So I'll get 1/2 times t squared plus 3 raised to the negative 1/2 times 2t. So there's a power rule and a chain rule in there. Y prime of t is equal to, now I'm taking the derivative of the natural log of t squared plus 3. That'll give me 1 over t squared plus 3 times the derivative of t squared plus 3, which gives me 2t. And then finally, z prime of t, well, z is just t, so z prime is just 1. Okay, now x prime of t naught is equal to well, let's plug this in. We are going to get, those 2's are going to cancel. The t on the outside is just a 1. So let's actually rewrite this. Instead of t naught, we're going to write it as x prime of 1 is equal to, and I get 1 times 1 squared plus 3, that'll be 4 to the negative 1/2. That's going to give me a 1/2. Y prime of 1 is equal to, I get a 2 in the numerator and a 4 in the denominator. That is 1/2. And z prime of 1 is equal to 1. So now I have a v vector. V is equal to the vector with components 1/2, 1/2, and 1, which means the tangent line is r of t equals r naught, which I said before was the point that was given, 2 ln of 4, 1, plus t times the v that we just found is equivalent to r prime of t naught, has components 1/2, 1/2, and 1. I can bring those together, get 2 plus t over 2, ln of 4 plus t over 2, and 1 plus t. And that is the equation for the tangent line to the curve. Now they want the parametric equations to that, and that just means, let's see, the parametric equations or parametric form is x equals 2 plus t over 2, y equals ln of 4 plus t over 2, and z equals 1 plus t. And we're done, finally. Okay, so that is our final answer right here. The parametric equations for the equation of the tangent line to the given curve. Okay, there's a lot of work in there. My hope is that with some of that explanation, it makes working through these a little bit more intuitive as to what you're supposed to do. All right, next problem. Sketch the plane curve with the given vector function, find r prime of t, and sketch the position vector and tangent vector, r prime of t, for the given value of t. Whew, that's a mouthful. Let's start with the very first thing. Sketch the plane curve with the given vector function. Okay, plane curve. I'm not sure how to graph that, so what I need to do first is write out my parametric equations and see if I can get this back into x's and y's. So my parametric equations are x is equal to e to the t and y is equal to 2t. It looks like I should be able to get what I need. In the x equals e to the t, I've got my t as a power. Maybe I could solve for t in there in terms of x by taking a natural log. So if I log this, I get ln of x is equal to t. Okay, now we're getting somewhere because we can take this, if t is equal to ln of x, we can substitute that into our y, and we get y is equal to 2 times ln of x. This is something that I can actually graph. So this is what they're after. So I'm going to get my graph down here. We're going to be putting a few things on here. So I'll try to draw it relatively nice. I actually don't need much of a negative side. Okay. Now the natural log function, when x is 1, we get 0. And we don't get a whole lot more better than that. Beyond that, the 2 is going to kind of stretch things out vertically because the 2 just is a doubling factor. So in general, we've got basically a natural log function. They all look a bit the same. All right, so that's good enough. Now let's see what's going on here. They're saying find r prime of t and sketch the position vector, r of t, and the tangent vector, r prime of t, for the given value of t. Okay, I have my plane curve. I'm going to look at r of t at t equals 0. If I plug in 0, I have r of 0 is equal to e to the 0 for the first component and 2 times 0 for the second component. That gives me 1, 0. So the position vector at t equals 0 starts at the origin and then moves over by 1 along the x-axis and stops at the point 1, 0. And it points there. So this is my r of 0. That's what they mean when they say sketch the position vector. Now the other piece, I need to find my tangent vector. So r prime of t is equal to, and now I take my derivatives, d dt of e to the t is e to the t, d dt of 2t is 2. And now I need this at t equals 0. So r prime of 0 is equal to e to the 0, 2, which simplifies to be 1, 2. Now here's what's different about the tangent vector. It is tangent at the point on the curve. We do not draw this like a position vector. In fact, we go over to the point where t is equal to 0. It's right where my position vector is pointing to, okay? So starting there, we go, the directions are saying go 1 in the x direction and go up 2 in the y direction. So starting at the point of tangency, that's the 1, 0, and then going over 1 and up 2 gives me this vector right here, which is indeed tangent to the plane curve. And this is all we have to do. In WebAssign, I believe these problems are, unfortunately, multiple choice. I would strongly recommend that you just work them out on paper like this, and then you should see your work as one of the choices. Okay, next. We have some properties about how derivatives work with vectors and then all those different operations. Focus more on things like how the derivative of a sum of vectors. So this is our sum property, the first one. The derivative of a constant times a function, bring the constant outside. So that's our constant multiplier, or in other words, our scalar multiplier. Now, these next 4, I will tell you, I don't really use them. That's not true. I use this one. I do not use these. I shouldn't just say don't. I just say I don't use these. Ever. But that doesn't mean you won't ever. Many of you are studying to be engineers, and these may very well come in handy, quite handy. The third one, though, comes in handy for me when we have a vector function and all the components have a common factor that I can pull to the outside. And then I have a scalar function, f of t, times a vector function, u of t. And interestingly enough, I end up having a product rule that is extremely similar to how things worked with regular functions. And so this is our product rule between scalar and vector functions. I actually use this one all the time when calculating the unit tangent vector and the unit normal vector. It makes the calculations so much easier. All right, well, let's see. Integrals. If we need to integrate a vector function, fortunately, all we have to do is integrate each component separately. Unfortunately, that means we integrate more than once. So let's go through one example. We have this integral. It's the integral from 0 to pi fourths of secant t tangent t I hat plus t cosine of 2t j hat plus sine squared 2t cosine 2t k hat, all with respect to t. So we get a dt in there. Now what I do with these, and you can do this too if you like, is I rewrite this in the angle bracket notation. I prefer it. I don't want to lose i's, j's, and k's. And then I distribute my integral to each component. Here's what that looks like. So big old angle bracket. First component, integral 0 to pi fourths of secant of t tangent of t dt, comma. Second component, integral 0 to pi fourths t cosine of 2t dt, comma. Last one, integral 0 to pi fourths sine squared of 2t cosine of 2t dt. Close the angle brackets. Now what I do is I go through and I number these 1, 2, and 3, and I deal with each one separately. When I have my final answer, I need to go back to my vector notation, but in the meantime, I'm going to work with these individually. So the first one, integral from 0 to pi fourths of secant of t tangent of t dt. Well, the antiderivative of secant tangent is just secant, right? Because the derivative of secant is secant tangent. So this gives me secant of t evaluated from 0 to pi fourths. So this is secant of pi fourths minus secant of 0. And remember, you can think of secant as 1 over cosine of pi fourths, right? Minus 1 over cosine of 0. Cosine of pi fourths is going to be root 2 over 2. So we have 1 over root 2 over 2, right? And so that's going to be 2 over root 2 minus, and then the cosine of 0 is 1, so we're just looking at a minus 1. Don't worry about rationalizing. It's fine if you don't. Although if you do rationalize this, it does simplify to just be root 2 minus 1. It doesn't make it more correct though, so don't worry. That's the first one. The second one, we have the integral from 0 to pi fourths of t cosine of 2t dt. Now this one brings up some old memories maybe of a method called integration by parts. Anytime we have a polynomial function times a trigonometric function, we'll have to use integration by parts. So down below here, I'm going to have my u is equal to and my dv is equal to. A wise decision for u would be the t, so that when I find du, I no longer have to deal with any variables. Du will just be dt. dv will be the cosine of 2t dt. And the antiderivative of that, let's see, so the derivative of sine is cosine. So we have to be dealing with a sine. And we would have to have a 1/2 sine of 2t in order to handle the chain rule that would come in the differentiation. So just working backwards, if I was to take the derivative of 1/2 sine of 2t, I would get 1/2 cosine of 2t times 2, and the 2 and the 1/2 would cancel out. So I have my pieces. Remember that the integration by parts is uv minus the integral of v du. So that's what we'll use. All right, uv, that's going to be t over 2 sine of 2t from 0 to pi fourths minus v du. That's going to give us the integral from 0 to pi fourths of 1/2 sine of 2t dt. All right, I'm going to do one more integration, then I'll evaluate all of them. Let me just kind of box this one off. All right, so this is equal to t over 2 sine of 2t. All right, I have a negative sign, and the derivative of cosine is a negative sign. So the antiderivative of negative sine would be a positive cosine. So I'll have a plus, and that 1/2 is there. So I'll keep that there. The antiderivative of sine of 2t, or negative sine of 2t, that's going to be a positive cosine of 2t over 2. So I get another 1/2 in there, cosine of 2t, from 0 to pi over 4. All right, substituting all that in, pi over 4 plugged into t over 2 gives me pi over 8. I have sine of 2t, so that's going to give me sine of pi halves, plus 1/4 cosine of pi halves, minus, the first term will be 0 because I have 0 over 2, and then minus 1/4 cosine of 0. And this simplifies. We are now left with, let's see, the second term, cosine of pi halves, that's 0. The last term, cosine of 0, is 1. Okay, we got it. Sine of pi halves is 1. So our final answer here is pi over 8 minus 1/4. And that's the third one. Or sorry, the second one. The third one is the integral from 0 to pi fourths of sine squared of 2t cosine of 2t dt. Okay. So I have one term that is squared and one that is linear. And I'm thinking I should probably be doing a u substitution, where u is equal to sine of 2t, because then du would be cosine of 2t times a 2 and a dt, but I can handle the 2. I just divide by both sides by the 2. So I get 1/2 du is equal to cosine of 2t dt. That makes things a little bit easier. So now when I write my equality, I actually don't have equality because this integral is a definite integral and I don't change my bounds. I always go back to my variable later on. So when I write this equal, it's kind of a question mark. Like, is this really equal? Because I'm going to write an indefinite integral. And then later on, I'll go back to my t bounds. So in this indefinite integral, I replace the sine of 2t with u, and there's a square, so it'll be u squared. I replace my cosine of 2t dt with a 1/2 and a du. And now I integrate. This is just going to give me 1/6 u cubed. And that is the value if I had an indefinite integral, and then I would put a plus c. I'm going to go back to t's though. So this in the end is equal to 1/6 sine of 2t. And the sine gets cubed, and I evaluate from 0 to pi fourths. All right, plugging everything in, I have the 1/6 on the outside. Inside, I have sine cubed of pi halves minus sine cubed of 0. Sine cubed of 0 is 0. Sine cubed of pi halves is 1. My final answer here is 1/6. Okay, so I'm going to go back up to my integral that was up here, and I'm going to call this integral I hat. Okay, for integral vector. It's a lazy way for me to be able at the very end say, hey, that thing that I named upstairs, here's what it's equal to. Okay, so my integral vector, after evaluating everything, I get components. In my first component, my x component, we got √2 minus 1. In my second component, we got pi over 8 minus 1/4. And in my third component, we got 1/6. And this is the value of the integral of the vector. Okay, so that is derivatives and integrals of vector functions. We will definitely be using this more, and as we go through more, we'll get more practice working with derivatives and integrals. Please reach out for help if you're struggling with either of them. It may have been a while since you've done integration or even derivatives, so don't be shy. Please get the help that you need. Thank you.